Hey everyone, this is Dr. Walker. In this video, we're going to do an example of finding the electric potential due to point charges. Specifically, we're going to find a potential due to a dipole at different locations. So this example has three parts. And you'll see that this is a lot easier than finding electric field since, as we discussed, potential is a scalar and you can just add it. So for the first part, we're finding the electric potential at point P on the y-axis. And remember, a dipole has a positive and a negative charge of the same magnitude, and they're separated by a certain distance. So to find the electric potential at point P, we can just write down the equation that the potential at point P is Ke, and then the sum of all the individual potentials. And in this case, we only have two charges, so we only have to add the potential due to the positive charge and the potential due to the negative charge at this point. So we know from the equation that we need the distance r between the charge and the point. That's going to be our distance r, which does happen to be the same for both charges since point P is immediately above the center. So let's go ahead and find that distance. We're going to use Pythagorean theorem. R is going to equal to the square root of a squared plus y squared, since the distance from point P is y. So we're going to have Ke times Q, and we don't square the r, it's just r, so square root of a squared plus y squared. And then for the negative charge, well, the potential produced by the negative charge is negative. So we're going to add a negative Q. The sign definitely matters when you are dealing with potentials. So it turns out that because we have a positive and a negative charge, both at the same distance from the points, that the two potentials cancel each other out and we get 0 for the potential at that point. So of course that would be true anywhere along the y-axis. Now for the next part, we want to find a potential at a point R on the positive x-axis, which is to the right of the negative charge, a distance x from the origin. So once again, we're going to just add up the potentials, but we need the distances. So the distance from the positive charge to R is going to be the A plus the x, so x plus a. And then the distance from the negative charge is going to be the whole x minus the a, right? This distance right here is x minus a. So now we're ready to add up the potential. So we can factor out the Ke, and we have Q over x plus a, and then we have a plus a negative Q over x minus a. So these do not cancel out, but we can go ahead and simplify. If we go ahead and multiply by, get a common denominator here, we see that this is a difference of squares, and we're going to end up, I'll go ahead and do the math. We're going to do Q times x minus a minus Q times x plus a all over x plus a times x minus a, right, where I multiplied both of these by x minus a and both of these by x plus a. And so now we're going to have Ke, we're going to have Qx minus Qa minus Qx minus Qa all over x squared minus a squared. And then we can see that these two terms cancel out, and we are going to get negative Ke, then we have 2Qa over x squared minus a squared. We do notice that the potential is negative, and see if you can think why that is. But it's simply because we're closer to the negative charge, so the negative potential dominates over the positive potential. And the third part of this problem is now calculate the electric potential at a point on the x-axis far from the dipole. And let's just assume it's in this direction really far, so at a distance of infinity. Or we can also think at a distance, this distance here is going to be x is much, much greater than a. So we can think of it that way. This point, let's call it point Q. So in this case, we can take our potential that we got last time, right? We got negative 2keqa over x squared minus a squared. And we can see that when x is much greater than a, then this a squared term basically cancels out, because x squared is just so much greater. So we end up with negative 2keqa over x squared. So we just took the limit when x was much, much greater than a to get our answer. So once again, we do get a negative potential at that point really far away.